In this video, we're going to talk about a very important equation. This equation is called the Henderson Hasselbalch equation. In this talk, I will discuss in two parts. The first part or first section, I will talk about the principles of the Henderson Hasselbalch equation. And the second lecture or second talk, I will discuss about the application of this Henderson Hasselbalch equation in human body. So let's dive into this very important equation. So hello, a warm welcome to all. So let us take an example in order to understand this equation. What will be the pH of the solution if 0.1 molar hydrochloric acid is poured in a solution of water? Suppose if hydrochloric acid 0.1 molar reacts with water, it forms hydronium ion and chloride ion. Now this is a strong acid. Now I've talked exclusively about strong acid in the previous classes, so if there is any if anyone wants to know something about it, you can go to my previous classes also. So in short, a strong acid is one which completely dissociates into its products. That means if you give 0.1 molar hydrochloric acid, it will completely dissociate with 0.1 molar of hydronium ion and 0.1 molar of chloride ion. Now if you want to know the pH of the solution, it becomes very simple because pH is negative logarithm of the hydronium ion. So because it is completely dissociated into the product, so we can take any logarithm. pH is negative, either hydrochloric is same or negative for hydronium ion, because as it is completely dissociated, it becomes a strong acid. Let us look at a second example. What happens when acetic acid reacts with water? Now when this acetic acid reacts with water, this is not a strong acid, this is a weak acid. So in weak acid, as I've already talked in earlier classes, the reaction is bidirectional. That means it does not completely dissociate into this product. So these are the reactants, this product. So there will be acetate ion plus hydrogen ion, but it is reversible. That is, it does not completely dissociate. So a forward reaction followed by a backward reaction. It will complete. It is very unstable. So it will again go backwards to form its acetate and water. So as you see from this side, again we come back to the equation, is that the acetic acid, as you see in the forward direction, it has become 0.0407 molar of acetate ion and 0.03 molar of hydrogen ion. This becomes the conjugate base of this acid. And on the backward reaction, as you see, it becomes 0.05 molar of acetic acid. It will simply dissociate into 0.6 molar. So if you want to say that pH is equal to minus negative log, or it will be very difficult because the values, as you see, are changing compared to strong acids. So because it is a reversible reaction, it doesn't completely dissociate in weak acids. So similar story goes for strong base like sodium hydroxide. Sodium hydroxide reacts, it completely dissociates sodium and hydroxyl ion, but then we can take an immediate log of minus negative log of sodium hydroxide to know what is the pH of the solution. But for the weak bases like ammonia reacts with water to ammonium ion, but it does not dissociate. So we cannot now say pH is not equal to minus log of nitrogen or sulfur. So in order to find out the pH of this weak acids and weak bases, strong acids was easy. We use the Henderson Hasselbalch equation. So what is the Henderson Hasselbalch equation all about? So that is the discussion of today's talk. The history is that it was first discovered by Lawrence Joseph Henderson in 1908, who derived an equation. He derived an equation to calculate the hydrogen ion concentration of the bicurrent buffer system. Now we'll talk about the bicurrent phase in subsequent classes. So he wanted to calculate the hydrogen ion concentration of the bicurrent buffer, and the equation looks like this: hydrogen ion into bicarbonate ion is equal to dissociation constant K into carbon dioxide and water. So he wanted to know the hydrogen ion concentration. What is the hydrogen concentration? This was given by Lawrence Joseph Henderson in 1900. This was followed in 1909 by Carl Albert Hasselbalch. He applied logarithm to this equation. Now logarithm really came out, and when he applied logarithm, he found that pH is equal to pKa plus log of conjugate base by acid for acid containing solution. So Carl Albert Hasselbalch devised this formula. So what does the derivation of Henderson Hasselbalch equation means? It gives the relationship now between pH, pKa and the concentration of weak acid and conjugate base. There is a relation. It gives a relation of what is the pH, what is the relation of pKa. We'll talk about what is pKa and the concentration of weak acid. So let us take an example. Let us take a weak acid like hydrofluoric acid. It reacts with water. So it's a reversal. The first step, it will go in the forward direction. It will form fluoride ion and the hydrogen ion. So these are called reactants on the left side, and these are called products. Now the rate of reaction we determine by how fast this reaction is going on is 4p1. So according to law of mass action, the rate of reaction is directly proportional to the reactant, that means hydrofluoric acid and water. So when we put equation, when we put an equal sign, it becomes V1 is equal to dissociation constant of forward reaction K into hydrofluoric acid and water. Now this is a reversal reaction. Now on a backward side, this will now have a backward reaction. This is now determined by a rate of backward reaction by V2. So now V2 according to again, V2 is directly proportional to fluoride ion and hydrogen ion, and V2 now becomes dissociation constant of the backward reaction is equal to fluoride ion concentration into hydrogen ion. Now when we rearrange this reaction, now this is a reaction reversal reaction V1 and V2. You see, this is weak acid on the forward direction, rate is V1, on the backward direction V is V2. So at equilibrium, what is when this V1 becomes, the rate of forward reaction becomes rate of backward equation. So if you rearrange this equation now, this rate of forward dissociation constant rate of forward reaction into hydrofluoric acid into water is equal to dissociation of the backward reaction to fluoride and hydrogen ion, and if you substitute this by an equation on both sides, divide both sides, we get the K is equal to F into H3O by hydrofluoric acid water. So and we put this K into water substitute reaction, we find that this K in water is nothing but the dissociation of acid is equal to fluoride ion and hydrogen ion divided by hydrofluoric acid. Now if you put logarithm on this equation, is log K is equal to log of hydrogen ion plus log of fluoride by hydrofluoric acid. Now substitute put negative on both sides of log, we find that negative log of this one is equal to negative of log of K plus log of fluoride ion. This logarithm of hydrogen ion is, we all know, is pH. This becomes pK plus log of fluoride by hydrofluoric acid. So we get one part of the equation. Now what is F by HF? Now come back to this equation again. Hydrofluoric acid when reacts with water, what will happen? This hydrogen ion, it gives hydrogen to water. So according to Bronsted theory, an acid is a substance which gives the hydrogen ion. So this now becomes the acid. Now because it has lost its hydrogen, what remains is the fluoride ion. Now whatever remains after the acid has lost its hydrogen, it becomes a conjugate base. We had all talked about very important topic of the conjugate acid and base. You can also go to my last lectures, and this becomes the conjugate acid. So or because this ionized becomes ionized form, and this becomes the ionized. So when you substitute this equation, pH is equal to pK plus log of fluoride by hydrofluoric acid, we get pK plus log of conjugate base by acid, or pH is equal to pKa plus log of, or our conjugate base is ionized form by the non-ionized form. So for a weak acid, similarly it goes like this. It becomes a weak base plus hydrogen ion. It becomes base plus hydrogen ion and water. Now when the backward reaction, what happens is that this BH lost its hydrogen ion, so it becomes hydrogen ion and base. So when you look at this, pH is equal to pKb plus log of BH plus B. This means that pKb plus log of conjugate acid by base. So thus for weak acid, what we find is equal to pH is equal to pK plus log of conjugate base by acid, and for weak base is pKb plus log of conjugate acid by base. Now after going through this answering this equation, we have looked for some scenarios. This equal, now we know that pH is equal to pK plus log of A minus HA, ionized form by the acid. Now what will happen if the concentration of this ionized form becomes equal to the concentration of the acid? That means if the substitute equation is that pH is equal to pK plus anything divided by the same becomes 1, so log of 1, pH is equal to pK plus 0 is pH is equal to pK. That means the pH becomes equal to pK when the concentration of the ionized form becomes equal to concentration of the acid form, or concentration of the conjugate base becomes equal to conjugate acid. So thus the definition of pK is, now we come to is that pH of the solution where both the ionized and the non-ionized fractions are present in equal concentration. Let us look at the scenario 2. Now what happens is, if pH is greater than pK, then means that if you substitute expression, that means that this part, this A by A minus log should be always greater than 1 at the most. That means A must be greater than A. That means the ionized form should be more than the non-ionized form. The ionized form should be, or the conjugate base should be more than the acid. Let's take this last scenario. What happens if pH is less than pK? That means the A minus, the concentration of the ionized form is less than the 100, so the ionized form is present in greater concentration than the ionized form. So this is all about the Henderson Hasselbalch in short. In next class, in the next talk, we'll talk about the application of this Henderson equation in human body. We'll talk how it helps us in regulation of the pH. Till then, I hope you all understand this class. Take care. Thank you so much.